Good afternoon. This is Rob Sin, and this is the last installment of new information this semester. So let me say something before we get started. I just want to say congratulations on test two. There were a lot of very strong performances on test two, and I'm really proud of you guys. Um, also, sorry about this. This is 22. I just screwed up. Um, but this is the last bit. We're going to talk about t-tests and hypothesis testing. So this launches right from where we were in the previous section that you just took a test over. So you were getting the idea in the last section that you went over about hypothesis testing. And so let me just say that the book has 4 phases or processes. I just think of it as 7 steps. And not everybody includes this one, but if you're reading a research report, you do need to identify the correct statistical procedure. So just tell people what you're running. Then you want to set up the correct null and alternative hypotheses, which the book did talk about as part of their plan phase. Verification. Now, every statistical procedure has a verification process whereby you check that the data are appropriate for that particular procedure. I'm going to go over the t-test verification in just a second. We're also going to set alpha. This is what we call our level of significance, and we're always checking to see if p is smaller than alpha. This step is where we run the test, and we need 2 things, a test statistic and a p-value. Then we're going to conclude and write down our statistical conclusion, which are either reject the null hypothesis, that's when p is smaller than alpha, or fail to reject the null, and that's when p is greater than alpha. By the way, there are lots of alphas, but they're all small. So about the biggest alpha you'll see in most cases is alpha equals 0.1. You will see them smaller, 0.25, 0.001, 0.025. But it's an introductory statistics course. You would have to go into a deeper level of stats before we're really going to talk too much about how to set alpha. Okay. And then the last step is we're going to make a research conclusion. In other words, we're going to take all of these results from, all of this stuff up here, and we're going to state it in real world terms. So let's talk about the verification process for T procedures. Now, the t-test was invented by William Seeley Gossett to improve upon the z-test, and he did make that improvement. And so much so that for large samples, when n is greater than or equal to 40, we don't even need to do data checks. That means that the t-test will hold up even if the data aren't bell-shaped, even if there are outliers, even in adverse circumstances, the t-test will work if the sample size is greater than 40. Now, we'll talk about this because there's 2 kinds of t-tests, 1 sample and 2 sample. When it's a 2 sample t-test, we're talking about the total. So if you had, I don't know, say 20 freshmen and 20 sophomores, that's a total of 40. So if you're doing a 2 sample t-test, that would in fact be a large sample. You put the 2 samples together for a 2 sample t-test. Now, for small samples where n is less than 40, we do need to check the data for outliers because outliers can mess us up and give us inaccurate results. So we're going to use a box plot for that. And as long as there are no outliers, we're good to go. If we do find outliers, then the data are not appropriate for T procedures. Okay, and then the last one is for tiny samples where n is less than 15. So not only do we check for outliers, because they can still cause a problem, anywhere under n equals 40, the outliers can cause a problem, but when we're also with a tiny sample where n is less than 15, we need to check a histogram to verify the data are approximately bell-shaped. And if not, the data are not appropriate for T procedures. So let's just scroll down here, and I've summarized for you all of this up here into sort of what I think of the t-test data checks, right? Large samples, n greater than or equal to 40, no data checks needed at all due to the robustness. That's a strength measurement for statistics. So really strong statistics are called robust, and the t-test, the t-statistic is robust. And small samples, it's still pretty robust, but we need to make sure there are no outliers. We're going to check a box plot, and then for tiny samples, we're also going to check a histogram. Okay, so the biggest cheating scandal ever for standardized educational testing occurred in, you guessed it, Georgia. Cheating can be found by searching for statistical anomalies. And the Atlanta Public School employees were changing incorrect answers on the students' papers to correct answers on the official score sheets, so the number of erasure marks on the test they doctored was too high to be the result of random chance. I actually read an article, and um, I did my best to be true to what actually happened. So what does a t-test do? A t-test compares a sample mean, or the mean of a subpopulation, to the mean of the overall population. Let's see how it works with the cheating example. So suppose that the Cheat Busters testing company knows that on average, statewide, the marks for fifth grade students is a normal distribution with an average of 8 and a standard deviation of 3. Now, I want you to notice this. What does this mean? Well, the capital N means normal, which just means bell-shaped. And 8 is the average, and 3 is the standard deviation. So if you ever see N parentheses, one number, comma, a second number, the first number is the average, and the second number is the standard deviation. And the N indicates that it's reasonably normal. Maybe not perfectly normal, but approximately normal. Okay, so that is our population. And I will point out that we do know our mu sub 0. It's right there. That's the mu for the population. Now, we have a subgroup or a subpopulation of 117 fifth graders in a school that's suspected of cheating. And the average number of erasure marks per exam was 9.5 with a sample standard deviation of 4. Do we have evidence of cheating? Okay. Well, let's take a look at the next page. All right, this is where you can see it a little better. And so we're going to compare the mean number of erasures to determine if there's a significant difference between the suspected cheating group and the overall population value. Okay, and we're going to test at the 0.1 level. All right, so let me pull up a graphing calculator here. So this will work on a TI-83, any version that's, well, I've got a couple weird versions, but most versions of the TI-84 and all versions of the TI-83. So those are legitimate calculators to use, and they'll look pretty much like this. So what I'm going to do, well, I need to turn it on. Okay, on, there we are. And then stat button, and I want to go to test. You see these three menus in all caps at the top: edit, calc, and tests. All right. So I want to go over to test, and you see t-test right here is option number 2. So I'm going to go to t-test. I'm going to hit enter. Okay. Now, they want to know what mu sub 0 is. Well, it's really nice because I happen to have mu sub 0 sitting right here, actually labeled as mu sub 0. So I can get in here. I'm sorry, let me get in here and change that to an 8. And then the X bar and the S are right here, the 9.5 and the 4. So 9.5 is my X bar, and my standard deviation is 4. And my sample size, if you remember, is 117. Okay. And I am interested in a greater than alternative hypothesis. Hang on just a second and let me do the first couple of steps, right? So this is just a t-test. And you can see the null and alternative hypotheses here, right? Mu equals 8, that's the null hypothesis if we're just in the population of Georgia, right? So why wouldn't this little subpopulation, which is in Georgia, be just the same as all the other subpopulations in Georgia and have a mu or a mean of 8? But what we're checking is whether or not this little subpopulation mu has a mean that's greater than 8, right? That's what we're suspecting. We're suspecting that that X bar, that sample mean of 9.5 is a little too high. Okay, so going back to our graphing calculator, this line here, this line right here, is the null hypothesis line. And we just make sure that the one that we select is the same as the null hypothesis, excuse me, the alternative hypothesis that we have. Did I say null? This is the alternative hypothesis line that I have marked here. Okay. And then we've got two options. We can either calculate or draw. And I like to draw. We'll see what happens. Rid of the marks. And you'll see that there is a tiny little bit of shaded area over here, but the area is so small that percentage-wise it just comes out to 0. So remember, P is a probability, and it's going to shade an area over here that's equivalent to this percentage of the area. Well, so let's just go back in to stat and test and t-test. I'm going to leave everything exactly as it is, but I'm going to go to calculate. So what happens with calculate? Calculate will give me a little more accurate p-value. Now you see that the p-value here is switched to scientific notation. All right, so this is 4 zeros, a decimal point, 4 zeros, and then the 4. So when you switch back over, oh, you'll see it here in just a second. Okay. Now you can see that that the test statistic and the p-value do in fact match what we had on the graphing calculator. I can pull it up here so you can see it. All right. But let me go back because this verification popped up. Well, this is really nice because we had a subpopulation size of 117. Well, that's much greater than 40. So that's a large sample. Large enough samples so that the robustness of the t-statistic is going to guarantee accurate results. We don't have to worry about outliers, which is good because we don't have them. All that we know about the subpopulation is this. We don't have the data. We just have the summary statistics of the data. So we really couldn't check it if this wasn't big. If this was a small sample or a tiny sample, we would need the actual numbers. You'll see one of those examples in just a second. Okay, so we ran a t-test. Now notice that we want to be very sure of our results. So we're testing at the alpha equals 0.0001. Wait, 0.001. And then notice this p-value, how small it is. That p-value, even though we're using a really small alpha, p is even smaller. So since p is less than 0.001, which is our alpha, we reject the null. And we have very strong evidence that cheating occurred. Okay, so this is one of the ways that these testing experts went about determining where cheating occurred, and then that would help inform who they needed to talk to in their investigation. All right, so that's just a straight up t-test. Now check this out. This is an independent samples t-test. And notice that we have those who said they were biological males and those who said they were biological females. So we've got two groups. Now notice that it says independent samples. What does that mean? That means you can't simultaneously be in both. Now, I'm gonna wash a whole bunch of discussion off the table right now and just say, look, you can be one or the other. And that was true for them. They took a survey where they could either choose not to answer or they could place themselves in one of two categories. So these individuals could in fact only be in one of the groups. Okay. Now notice the male sample, we actually know that n is 74 and the average is 30 and the standard deviation of 5.7, and we also have 130 and 28 and a half and a standard deviation of 4.9 for the females. Okay, but our research question says who's more optimistic. Okay. So the procedure is an independent samples t-test. And notice what we're doing here. We're naming the group. And by the way, so the book a lot of times will name them group 1 and group 2, group A and group B. That's fine. I named them M and F because we're talking about biological males and biological females. Okay? And the null hypothesis is that the two groups have equal means. Okay? We all are North Georgia. These were a bunch of, all of these survey questions come from North Georgia students. We were doing this a lot around 2011, 2012, 2013. So if you have older siblings who were there, who were at UNG, then they could possibly be involved in some of these surveys. Okay, so, but look at the actual research question, because you don't make the alternative hypothesis based on some, you don't you don't data snoop to see, oh wait, the average here is higher than this average, so I'm going to use it. No, I'm not going to use a greater than. What am I going to use? Well, it says who is more. Okay, so I'm going to use the not equal to alternative hypothesis, and that's really important, that you don't go data snooping for hypotheses. You come up with a hypothesis before, as the book says, while you're planning your statistical analysis, right? You come up with what your hypothesis ought to be. All right. Once again, verification. We're in a beautiful situation where we have 130 biologically female, 74 biologically male. If I did my math right, that's 204 total. So look, when we have a two sample t-test, right? When there are two samples, I'm taking the total of the 74 plus 130, right? So I'm taking the 74 and the 130, adding them together to get the 204, and that's what I'm using to determine if I have a large, small, or tiny sample. Now, since I do have a large sample, I do not need to do data checks. No data checks are needed due to the robustness of the t statistic. It's okay to proceed. Okay, so let's run this test. Once again, I'm going to grab my graphing calculator and I'm going to turn it on. I'm going to go over to the tests menu, and calculate will do things like it'll calculate the stats for data that's been entered. It'll do linear regression and so forth. On the test menu, that's where I can find this. And notice the z-interval. I can even do confidence intervals, t confidence intervals on my graphing calculator. Okay, so let me go back. Oops, sorry. Go back up to the top. You see t-test number 2, and then look at number 4. Two sample t-test. Okay, that's the independent samples t-test that I want. Okay, so I'm going to hit enter. And you have two input modes. Data input mode means that you started off with data. So if I go to stat button and then edit, I have these hotkey lists. And if you look above the one key, I have blue. I have a blue L1, a blue L2, a blue L3. So I have hotkeys that I can quickly access in these stats procedures. But you'll notice I don't have the data. I just have the sample data. Okay? So when I start running my two sample t-test, I'm going to go to stats mode. Okay. Let's see. So the male's 74. Let's see, 35.7 and 74. So 35.7 and 174, and then 28.5, M4.9, and 130. Okay, so there's a lot more room, so this test actually takes up more than one screen, but it also has a alternative hypothesis line. You see they're doing mu1 and mu2 for group 1 and group 2. And we have a not equal to over here. So I'm going to hit enter just to change, right? So you can scroll across there, and whenever you hit enter, it changes to the one that's blinking. Okay, now pooled equals yes or no. We're always going to use the pooled equals no. It's a more modern version that's harder to do by hand. So the yes is left in there in case people are taking a stats class where they have to do this by hand. But we're going to use no. And we're going to draw and look at the shading. Okay, so it's shaded a little bit over here, and it'll shade a little over here. Why? Well, because we're using a two-sided hypothesis, right? We used a two-tailed hypothesis. So it takes the total of about 6.06, and it puts about 0.03 over here and about 0.03 over here. But the total is 0.0597. Okay, and there's our test statistic. The t-value is 1.8993. Okay, so when we run the test, and again, they had said, hey, test at the 0.05 level. So we have, yes, we're testing at the 0.05 level. And we just wrote down exactly what the calculator said. Except I didn't. I made a mistake here. So this should be 1.899. Sorry. Just all right, sorry. So the t-value was 1.899, as you and I can both see right here. So my apologies on that mistake on the slide. And did I get the 0.423 right? Oh my goodness. So I got this way off. So this is 0.05, what, 9697. My mistake. Okay, and let's roll forward. See, now I got the p-value right here, but not right above it. That's interesting. All right, so at least I was looking at the right problem when I was doing the prep work for this lecture. So the p-value is just slightly bigger than 0.05, but we fail to reject the null. Notice that if it is bigger, even just slightly bigger, we fail to reject the null hypothesis. And what's the real world conclusion in that case? No evidence for a difference in optimism between those who are born biologically male or biologically female. All right. So that's a two-sample t-test. Okay, our final example today is what we call matched pairs. Now, what does it mean to be matched pairs? Well, the most familiar matched pairs design is a pretest versus post-test, right? You give somebody a test, you do some training, and then you give them, they retake the same exact test. This might be the Corps of Cadets doing a PT test during Frog Week, and then they train the frogs for 2 or 3 months, and then right before Christmas break, let's say, they do another PT test to see how well the frogs have improved or not. Now, in this case, the following data shows stress levels for a group of North Georgia females during the 2nd week of school and during the 7th week of school. Now, the 2nd week of school, the guess here was that there weren't many papers and tests due yet in the 2nd week. But in the 7th week, that's when it's right about midterms. 7th or 8th week is midterms, and that's when everybody's got tests and papers due and that sort of thing, a lot of deadlines. So the idea was that the stress levels would be higher on the post-test than they were on the pre-test. And we're supposed to test at the 0.05 level for a significant increase. Okay, now the thing to notice is that this is a single student. So Amy or whoever it was scored a 12 on the pre and a 13 on the post. And this is another student. They actually got less stressed at midterms. This is another student. Okay, now I had to offset these lines so the 8 and the 9 go together, the 14 and the 12 go together. So you can kind of see what the data look like there. Sorry about that. I just had to squeeze it all onto one slide. So what are we going to do? You're like, well, there's two samples, pre and post. So I'm going to do a two sample t-test just like you did before. Well, no, you're not. So this is kind of the key point of today's lecture is that with this matched pairs or pre-test versus post-test, and by the way, what other matched pairs are possible? You can do like reaction times with somebody's dominant hand and their non-dominant hand. And then what you're looking at is not their actual reaction time with their right hand or their left hand. It's you're looking at the difference between their dominant hand and their non-dominant hand. Okay. So what I think of when I have pre and post is I think of having a gain score. Sorry, I'm not great at writing with this pen. All right, and gain equals post minus pre. Which makes sense because if on the first test you make a 70 and on the next test you make an 80, you went up 10 points. Your gain is 10 points. This also works if it's negative. You scored an 80 the first time, but only a 70 the second time, you have a minus 10 gain. So negative gains are scores that went down. All right. So we're going to do a t-test on the gain scores. And this is probably going to be awkward when the rest of the writing on the slide appears, but we'll try it. So notice what I do. I have a little mu sub g. Now the subscript is not necessary here. Most people will just do this with a mu. Why do I put the mu sub g? Well, just to remind everybody in the class that I'm working on the gain scores, the average gain. And if the treatment had no effect on the scores, the gains will be 0 on average. Some people gain a little bit, some people lose a little bit, but on average, the gain would be 0. Okay, what are we looking for? Well, we're looking for a positive gain. We think that stress levels will go up because of this midterm time when stress should be a little higher than maybe the second week of classes when everybody is still just getting settled into a routine. Okay, now notice that there are 22 numbers in each list, right? So the pre-test list has 22, the post-test list has 22, but they're not independent. As a matter of fact, they're the same people. The same people have scores in each list. So this is dependent samples, or what we call matched pairs. All right, and so there's only 22. And since there's 22, we do need to check for outliers. Okay, wow. So what are we gonna do? Let me pull up the calculator. I'm not gonna make you watch me put all this data in, but I am gonna have you, I'm gonna have you see where I'm starting. Okay, so I'm going on Stat button, Edit menu, and number 1 option, Edit, and it brings me into this data editor. Okay, and this is list 1 right here, the 12, 16, 12. Okay, so I'm gonna go 12, enter, 16, enter, 12, enter. And I'm gonna finish entering this data. I'm just gonna do it off camera. I'm gonna pause the recording so you don't just have to sit here and watch. I'm just using the right and left arrows. So here I just use the right arrow. It pops me over to the first number in L2. So now for L2, I need 13, 13, and 16. So 13, enter, 13, enter, and 16. Okay. And in just a second, I'm going to pause this and I'm going to finish putting all the data in. And if you have time, you might want to pause too and get this data into your graphing calculator. Okay, so now I'm done. I've put all of these numbers into list 1 and list 2, and I'll scroll down here. You can see that I do in fact have all the data. I have the 8 and the 9, that's here, then 7, 10, that's there, then 7, 9, and 18, 18, 7, 9, there's the 18, 18. And so all the way down, and notice that it allows me to see the sample size, right? I said the sample size was 21. It looks like the sample size is, I said the sample size is 22. It looks like the sample size is 21. So maybe I miscounted. Sorry about that. Now what I want to show you is, well, yeah, these are two samples, and I could run a two-sample t-test. That's not the appropriate one to run. Let me show you how to do the correct one. So what's really nice in our graphing calculators that works a little bit like an Excel spreadsheet, I have a little formula I can write. So you see this black backlit area. If I go up, it highlights the L3, and then down here in the input line, it gives me the L3 equals. And I'm allowed to say what I want. Well, if you remember, gain equals post minus pre. So my post is in L2, and my pre is in L1. So what I want is L3 equals second L2 minus second L1. And when I hit enter, it fills in the third column. And these are my gain scores. Okay, so you can see I scrolled to the bottom because there are a bunch of positive ones at the bottom. And you see some negatives and some positives. Okay, but those are my gain scores. All right, so let's just go back to this part right here that shows check for outliers. Okay, well, the first thing I need to do is do that. So remember though, our gain scores are in L3. All right, so what I want to do is go to my stat plot. So second y equals, right? And I'm going to go into my, notice that they're all off, right? Plot 1 is off, plot 2 is off, plot 3 is off, 4 is just plots off. Okay, so I'm going to go into plot 1 just by hitting enter. I'm going to turn it on. And I'm going to go to this little outlier checker. And you see this is a standard box plot without the outlier checker turned on. And this little one where you see the little two dots out beside the right, past the right-hand tail there, that's the one that checks for outliers, okay? And it says X list and Y list. What the, oh wait, let me hit enter. Okay, there we go. Now it's just asking for X list. So I go second L3 to turn on the X list. And then I like using the plus sign as a mark, although it defaults to a box, which is also good. Okay, and then I'm gonna hit zoom 9. Why? Well, if you, oops, I just messed up. Let me try to get this back. If I go to zoom, oops, zoom 9, you see zoom stat. What it does is it zooms in on whatever stats plots are active, okay? And this is gonna let me know whether or not there are actually any outliers over here. If I just hit graph, if I just hit the graph button, the settings from the last stats graph I ran will be available. So what hitting the zoom 9 did was it zoomed in on exactly the data that I have in here now, and that means it goes from min to max. And that means that if there were any outliers over here, or there were any outliers over here, I'd see them. Since I'm not seeing them, I'm deciding that it's okay to proceed. Okay, so I'm gonna go check. right? I did this verification. I checked for outliers. There are no outliers, so it's okay to continue. Oh, so perhaps this is where I got my t-values and p-values. All right, so stat button, test menu, and I'm going to run a t-test. So again, dependent samples t-test or a matched pairs t-test is just a one sample t-test on the gain scores on the list of differences. We're now ignoring the pre and post, and we're just looking at the gain. All right. So to t-test, enter. Now remember, with our data in L3, we want to use data input mode. We want to use 0, right? Remember, 0 gain is our null hypothesis. We're going to have it point at L3. And we have a greater than hypothesis here in our alternative hypothesis. So we're going to switch over to here on our graphing calculator. Alternative hypothesis line. So enter. And then let me draw it. And you'll notice, yeah, it's got the it's got the box plot superimposed behind it. Ah, yes, 0.1974. Yeah, and 0.423. Yes. So I rounded a little bit, but those are the correct values. Good. But notice our p-value, way larger than our alpha. So since p is greater than 0.05, we fail to reject the null, and there's no evidence for an increase in stress. Now that's kind of crazy. Now it turns out this was during a time where people were getting their schedules dropped for non-payment when they didn't have any controlment. They hadn't gotten. Well, anyway, I won't go through the whole drama, but it was a mess, and the university worked hard to change things. Um, but the second week of classes was apparently pretty stressful back then, just as stressful as midterms. That might be different. We might get a different result today if we ran the same kind of test. But then, and again, you got to remember this with statistics on the test, go with what the statistics say, not what you feel must be true. You're like, oh, the post test has to be higher. Well, wait till you see the statistical results. And if the p-value is big, then we're going to fail to reject the null. So what are we rejecting? We're rejecting the null. Excuse me, we're failing to reject the null. We're saying the gain may have been 0. There may be no difference between the pre-test and post-test scores. Okay, so that's all I have for you. That's the t-tests. So remember, you can use a graphing calculator on all of the last two tests. So I suggest a TI-83 or a TI-84 because, well, anyway, that's what I'm using in the video. That's what I use, to teach the class. Uh, and it's perfectly fine if you need to borrow one from somebody when you're taking the test so that you have access to that. So, what do you need to know? Okay, I will say this. You don't need to know everything on this list. Let me just run back up. You should know the basic idea of how these hypothesis testing steps go. But you're not going to have to write one. It's in a normal stats class, this is kind of like an essay question where you get the blurb at the top and then you have to do all 7 steps. Well, that's not how it's going to be. This is going to be a multiple choice test. So you need to be able to put the data into your graphing calculator and get a t-score, a t-statistic, and a p-value. You need to know based on data whether or not you should reject the null or fail to reject the null. So if they give you some data and an alpha value, you should be able to put that data in your graphing calculator, run the correct test, and see if the p-value is less than alpha. Okay, and like you did on the last test, there won't be as much of it on this test, but you should know how to set up your null and alternative hypotheses. Maybe I should, this step. And verification is important, but not difficult. So again, know how to do, know the basic outline of the steps, but know how to do those things I specifically spoke about. And also remember, there are 2 worksheets in D2L with solutions. Just scroll all the way to the bottom and you'll see that there are solutions. I think it's on page 3. I think pages 1 and 2 are problems and page 3 is solutions. So a test statistic and a p-value is given, the correct statistical conclusion is given. So be sure to do some homework in D2L. Borrow a graphing calculator if you need to, or grab your graphing calculator and go through those examples and make sure you're doing them correctly. If you have any questions, please hit me up on Teams and I'll talk to you soon. And again, one more time, congratulations on test 2. The class as a whole did a very good job. Have a great day.